Hi, my name is David Terr, and the title of my talk is An Introduction to Separable Differential Equations. I'm going to start with a definition, then I'm going to give you an outline of how to solve separable differential equations, and then I'm going to give several examples. And the examples I'm going to give are Malthusian population growth, compound interest, and radioactive decay. We'll start with a definition. The separable differential equation is a first-order ordinary differential equation of the following form. We have dy dx equals f of x over g of y, where f of x and g of y are integrable functions of one variable. Now I'm going to give you an outline of how to solve a separable differential equation. Well, to solve the equation that I wrote down previously, what we do is we start by multiplying both sides by g of y dx, and when we do that, we obtain the equation g of y dy equals f of x dx. So you'll notice that the variables x and y are separated. That's why they're called separable differential equations. So the next step is to integrate both sides of this equation. And when we do that, we get the integral of g of y dy equals the integral of f of x dx plus an integration constant, which I call c. Now that I've explained how to solve a separable differential equation, I'm going to start giving some examples. So the first example I'm going to give is Malthusian population growth. This is a simple population growth model given by the differential equation dp dt equals kp. So what that means is that the rate of change of population is proportional to population. So p of t is the population of given region at time t, and k is the population growth rate. So how do we solve that separable differential equation? Well, what we do is we use the same technique I showed you earlier. We separate the variables, and we do that here by multiplying both sides by dt over p. And when we do that, we get the differential equation dp over p equals k dt. So you notice that p is the variable p is on the left and the variable t is on the right. So the next step is to integrate both sides of that equation. When you do that, you get the integral of dp over p on the left, and you get the integral of k dt on the right. And when you solve those integrals, you get the natural logarithm of p on the left, and then you get kt plus c on the right. Remember, you always have an integration constant. So then the next step is to exponentiate both sides, and when you do that, you get p of t on the left, and you get e to the kt plus c on the right, which you can also write as e to the kt times e to the c, and you can call e to the c p0. That's just another constant. So you get p of t equals p0 times e to the kt. Here's a simple example of Malthusian population growth. We have a country with a population of 20.0 million. Its population is increasing at a rate of 2% per year. So we want to know what the population of this country is going to be in 10 years, in 20 years, and in 50 years. Well, we just used the equation we just derived for the population at time t, and we have p of t equals p0 e to the kt, and we know what p0 and k are, so we just plug in those numbers. We get 20.0 million times e to the 0.02t. That gives us our population at any time t, any number of years after the starting time. So after 10 years, our population is going to be 20 million times e to the 0.2, which is 24.4 million. After 20 years, the population is going to be 20 million times e to the 0.4, which is 29.8 million. And after 50 years, the population is going to be 20 million times e to the 1, which is 54.4 million.